All right, this is another problem review. Creeping flow between two concentric spheres. Very viscous Newtonian fluid flows in space between the spheres. As shown in the figure, it is desired to find the flow rate in the system as a function of the imposed pressure difference. Importantly, neglect affects and postulates that neglect and affect postulates and say that v theta depends only on r in theta, which and the other velocity components are zero. So that's going to be important for some of these problems. All right, part A. Use the equations of continuity. Show that v theta sine theta equals is a function of r, basically. So yeah, let's get to it. So we got the equation of continuity, B.4-3, and that's for spherical coordinates, obviously. Yeah, so this is the equation of continuity for spherical coordinates. This is table B.4, page 846. All right, so yeah, so equation of continuity, basically getting rid of the radial velocity, saying it's steady state, no phi velocity, and so we're left with this equation here. And then this explanation is not the greatest, so I just added another explanation. I'll get to that in a second. All right, so yeah, we're back at this equation. So first, you want to multiply over r sine theta, and that's because even though theta is dependent on, or sine theta is dependent on theta, it's not within the derivative, so you can still multiply it over even though it's going to get rid of that information. So if you can't multiply over these because they're within the derivative, but you can multiply this because it's outside of the derivative, basically. Also take out theta from the derivative, so just move rho out of the derivative, move this rho out, and then also just divide it out because again, it's not dependent on, well, it's in the theta derivative, but the density is not dependent on theta, so you can just take it out because one side is equal to 0. So now you're left with this equation, and this equation basically just says that dd theta or dv theta, not just d theta, dv theta d theta equals 0 because this whole derivative equals 0. So then that'll go on with another piece of information. So then you separate and integrate this equation up here, and you get v theta sine theta equals c1. And since the problem statement says that v theta is only a function of theta and r, and we previously proved that dv theta d theta equals 0, that means that it's only a function of r only. So then this separation integrate, this c1 must be a function of r. So we're just saying c1 is an arbitrary function that's a function of r, and that function equals this here. So that's part A. That's the answer for part A. All right, now into part B. Wants you to write the theta component of the equation of motion for the system, assuming the flow is slow enough that this term is negligible, which is basically just the non-constant viscosity term, basically. So yeah, again, we want to use, we're going to use this equation here, and that's because this is g theta. This is the direction we're interested in because we're looking at v theta, and also we're in spherical coordinates, and we're using b.6 instead of b.5, and that's because the problem statement said it's a Newtonian fluid, so we can say the density and viscosity is constant as a result of that. So we're using b.6-8, and that's on page 848. All right, so yeah, equation B. So yeah, this first thing, we're crossing that out because we're assuming a steady state, crossing out this because no radial velocity, crossing this out, again, because of the equation of continuity, where we said dv theta d theta. Again, this thing right here is right. Just d theta is not necessarily correct. But yeah, so that's why we're crossing this out, because this is phi. Sorry, I kind of mix those two together, but this symbol here is phi. So yeah, there's no phi velocity. From the equation of continuity, well, actually, no, this I guess just doesn't get crossed out, but Um, I think it does actually get crossed out because the problem statement says v theta is only a function of theta or r. So this does get crossed out. I think I cross it out later, but cross out VR because there's no radial velocity, cross out V phi because there's no phi velocity. Leave all this alone. Again, cross this out again because of the equation of motion. We said that we said basically that that's equal to 0. Oh wait, does that make sense? Yeah, I think you do. You do cross that out, because this whole equation equals 0, so you can say this equals 0. Cross this out because, again, v theta does not depend on phi. Cross out this because there's no radial velocity. Cross out this because, again, no v phi. And the gravity term stays, and that's because as phi is changing, when you look at the problem, or when theta is changing, theta is in the direction of like gravity. So, yeah, that makes sense. And yeah, in a sphere, theta is like this coordinate direction, and phi is like this coordinate direction around the sphere. So it's kind of important to know. Yeah. All right, so write out the simplified equation. So we're left with this equation, and in part A it says that v theta sine theta is a function of r. So we can solve for v theta and this equation and plug it in here basically. So yeah, insert definition for theta in the equation of motion and take sine theta out of the derivative because it is not a function of r. So we're taking this sine theta and bringing it out here with this transformation here. All right, so now a kind of non-standard definition for partial or complex. Is it complex pressure or is it it's modified pressure? Complex definition for modified pressure, and that's because we're working with v theta. So if you want to look at this, 2.3-10, this weird definition. So complex pressure conglomerate equals P0 minus rho g, length equals 0, minus PL, the pressure at L, minus rho g at height equals L, all divided by L equals this conglomerate. And the general definition is usually this. And this L is from, you can multiply this over and it's P0 minus PL equals rho GH basically, or so basically delta P equals rho GH, and that's like a pretty like very standard definition of like pressure, like what pressure is. So this is negative delta P, and that's because the derivative is the final value minus the initial value, and this is the initial value minus the final value. So negative delta P equals, so you flip this around, negative delta P equals negative rho GH, and we're saying that L is the same as H. So yeah, so basically modified pressure is those two quantities kind of combined. And the reason in this equation that it's not just the standard this or negative dp d theta, why there's a 1 over r here, and that's because v theta is basically the change in, how do I put this definition, is inserted for these two expressions here. Hopefully I can come up with a better explanation, maybe in a clip or something, or like pasting stuff on the screen. All right, so now we're going to manipulate the equation so that each derivative term only has So that each derivative term only has the terms that the derivative is dependent on within it. So we had this equation, or I think we're just so we're just moving basically we're moving this to this side, and we're going to move this equation to this side, and we're going to bring the sine along with it, because sine theta along with it, because this is dependent on theta. So yeah, move the sine, multiply by r to just to get rid of it from this. So from the why do I multiply by r? Oh yeah, to get rid of this r here. I get rid of that because it's along with the theta, and I don't want that. So yeah, multiply by r, multiply by sine theta to get the sine theta along with this, and then we set them equal to each other. I just move this equation to the other side basically. And because there's only one term on each side, we can separate each side and set them equal to some arbitrary constant. So this is because there's only one derivative on each side of the equation. So I mean, technically, you could do this with like if there's or like one derivative conglomerate term. So like this still counts, but so like if there was derivatives added to each other, you could still add it to each other on the same side of like, or like two derivatives that are added to each other on one side, two derivatives that are added to each other on the other side. You could still separate them out and set them equal to the same constant, but it wouldn't be very useful because it's still difficult to separate and integrate. Whereas in this case, when there's only one derivative, you could just separate and integrate easily. You just move the d theta over to this side, keep the d partial pressure on the side, and you can just separate and integrate like a normal thing. And then once you basically you solve for b for both of these equations, and you'll see basically. So yeah, first thing we're going to do is we're going to separate and integrate this first expression, number one here. Look at the coordinate system and figure 3B.4 d theta integral goes from epsilon to pi minus epsilon. So again, this here is epsilon, this coordinate here is epsilon. So it's going from pi up here, this is pi, to pi minus epsilon here. And this is not part of the coordinate right here. So from pi to pi minus epsilon. And yeah, the theta direction is like the up and down direction, and the phi direction is like this direction around this, like this direction around the circle. So that's where that comes from. So yeah, we're just separating and integrating. Sine p equals that. I don't know why I got rid of the. Oh, I guess I just divide the sign out. Oh yeah, I divide the sign to this side as well because the d theta is on this side, so the sign has to be on that side when you're integrating. So yeah, this one's pretty simple. It's the partial pressure or the modified pressure on each side, and then this is kind of gets annoying. Like you just look up identities or like basically integral definitions. Like it's kind of hard to just know what these integrals are going to be. One divided by sine theta, integral of that. Who knows, man? I just look it up, or I just do TI-89 can do it, which it gives you this definition, which is different from this, but this is simpler. Or Symbolab or Wolfram Alpha. I would suggest one of those because it's just easier. And so you get this expression. And yeah, that's just pretty standard. You're just plugging these in. That's pretty simple there. And then you use a definition to combine them. So ln x minus ln, or log definition to combine them. Ln x minus ln y equals ln x over y, and that's the same for any log. Like, it's the same for log base 10, log base e, whatever. So yeah, that's what we do here. And then we got another sine, cosine, cotangent identity, which is just terrible. So yeah, tan pi minus 2 minus epsilon minus 2 equals cotan this. So yeah, so this is cotan epsilon over 2, and then this is tan epsilon over 2. And then we have another sine cosine simplification. This one's kind of easier though, because it's just tangent equals sine over cosine, cotangent equals cosine over sine, and then you're just multiplying them. So this is cosine over sine in the numerator, and this is sine over cosine in the denominator, but it's inverted because it's in the it's in the denominator. So it's normally sine over cosine, but since it's the denominator, it's cosine divided by sine, and then you just get cotan squared over that. So, or from simplifying that, and you can replace this with cotan squared, and you solve for b, which is simple from there. All right, so now we're integrating and separating the second condition with no definite bounds. I don't know why I'm doing that, but I guess I'm doing it with no definite bounds. And that's again this equation here. I think this separating and integrating thing helps with the no definite bounds somehow. I kind of forgot. So yeah, you only need one integration. Constant for integration of both sides. Why do you only need one constant? Oh, well, yeah, you only need one constant for integration of both sides. That makes sense. Integrate a second time, and you get UR equals that. So integration boundary conditions are both law of the wall boundary conditions. At R equals big R, V theta equals 0. At R equals KR, V theta equals 0 as well. So that's back to this here. R equals KR. It's the law of the wall. It's moving at the same speed as the sphere, so the sphere is not moving, so it's velocity 0. At R equals big R, again, same thing. It's at the wall. The wall's not moving, so velocity 0. All right, so part A, we could see that UR equals V theta sine theta, so UR will equal to 0 at both boundary conditions. V theta is 0 at both those boundary conditions, so UR will be 0 at those boundary conditions. That makes sense. All right, so now you're employing the boundary conditions. First one, at R equals big R, V theta equals 0, so you plug in. Basically, you plug this expression in here, and you plug in the radiuses for here, and so it's 0 because for both the binary conditions, this expression is going to be 0. So we're using with big R, BR equals this, that, C2 equals that. So now you're employing the second boundary condition. Same thing, you just plug in KR for this equation up here, and you set this equal to 0 again because this expression is 0 for both boundary conditions. Solve for this equation, and then we plug in I plugged in C2 for this equation, it looks like, before I even did anything. So I just plugged in this for here and this boundary condition exposition, I guess you could call it. So now you just solve for C1. And there's my algebra, and C1 equals that. Multiply by KR in the numerator and denominator. Again, this is kind of just to make it cleaner and stuff. Factor at the numerator, definition. It's just making it, I think it's more just to like match what the answer finally gives in the textbook. So you got to kind of make it neat for in all steps of the process. So you're just doing, I don't know, you could read this. It's basically just geometry shit. Plug in C1 into the definition for C2, found with first boundary condition. Yeah, factor. It's pretty simple, self-explanatory stuff. Plug in C1 and C2 back into the integrated equation. Woo! Okay, so yeah, you do that. You just plug in C1 and C2 back into not that equation. Oh yeah, that equation. Plug in C1 and C2 back into this equation. Yeah. So UR equals this. Vector out BR over 2 mu. Again, all of this is just to make the equation prettier so it matches the textbook answer. Factor out K in the parentheses for the terms that have it. Again, making it pretty, making it pretty. Insert the other found expression for B into the above equation. So we're we're just trying to get like B alone, like in one term by itself. So I think that's like the main purpose of doing all this simplification BS. So yeah, B, plugging B in. So yeah, that's again why we need both the sides of the equation, I guess. So we're solving for B in two different things, and then we have B in terms of just the equation parameters and not just like there's no B in the equation. So we're having this equation with B and like an outside, like one single term, isolating B in the equation basically, and having U as a function of R on the other side of the equation. And then we could just plug in B and it'll look somewhat neat. So now we just need to convert this to 3B.4-5, which I'm pretty sure is just the answer to the problem. 3B4-5. Yeah, okay, so yeah, this expression for B also matches pretty much, I think. No, it doesn't match exactly. I don't think. Does it? I think you could just put 2 out front here and it works somehow. I don't know. Makes sense. Yeah, so that's how you get rid of the square. Log roll x squared equals ln x plus ln x equals 2 ln x. That makes sense. I mean, that was pretty obvious, but I'm just an idiot. Yeah, so that's where the 2 comes from. And you get the 4 there. Put the 4 here, same as 3B4-5. Yeah, 3B4-5. So now, so now use the results above to get the mass flow rate. Oh yeah, so epsilon. Yeah, okay, never mind. Okay, keep going. So, oops. Use the results above to get the mass flow rate that. So basically, this is just an integration type thing. Just going to be somewhat annoying, but not too bad. So mass flow rate is rho times V times A, and that comes from V times A is the volumetric flow rate, because when you think about it, velocity meters per second times area meters squared, that's meters cubed per second. So that kind of makes sense for volumetric flow rate. And then you multiply the volumetric flow rate by density, which is kilograms per meters cubed. So the meters cubed cancel, but the kilograms on the top stays and the seconds on the bottom stays. So it's kilograms per second. And that gives you the flow rate, which is denoted by W or some other really weird way of saying it. But I know there's like a weird way to say the symbol, but I kind of forgot what it is. So average velocity is the integral of the velocity over the area, which is like the total velocity like profile over the area, but then you have to divide it by the area. And the area and the D area, the differential area, are both areas that are perpendicular to the flow direction. So perpendicular is like the direction that's looking straight at a wall. It's like It's like T-boning. It's like a T-bone, like two cars T-boning, I guess. You probably already know what it is, but I don't know why I'm even explaining it. So mass flow rate is W, and so yeah, and the areas. So when you do the mass flow rate, it's like average velocity times area times average velocity times area times density. So the area the area in the denominator of the average velocity expression is canceled out with the area for the mass flow rate. So mass flow rate is just rho times the integral of VdA. So from this chart we can see that differential area dA with respect to theta direction, which is our flow direction, equals r sine theta dr d theta. Okay, so or dr d theta, or is it d? No, yeah, it is. It is d phi. Okay, so let's go to Google Docs. All right, so I finally figured out how this actually works. All right, so the reason the differential area is for a sphere is r squared d theta, or r squared sine theta d theta d phi, is because so basically the circumference of a circle is or like the circumference of a segment of a circle is a function of the radius of the circle, and then also the the percentage of the theta around that it is um, out of 2 pi. So this circle here, like imagine this is a circle that's going around here. Its radius is r sine theta, and that's because this is the radius here, or this is the radius here of this here, and this length is r sine theta because this is r, and this is the longest front length of triangle. This is theta, and so the opposite side of that angle is r sine theta. That's just because sine definition, first of all, and so that's the radius of this circle here, and the perimeter of this section that it forms is this length times d phi, which is this here. So normally it would be the circumference of the circle would be r sine theta times 2 pi, but if you just want this segment here, it's r sine theta times d phi, which is just this little segment of the circle here. So that kind of makes sense. And then it's kind of the same deal with here. So this radius for this side length, radius by itself just represents the radius of the circle. So this circle goes like around like here basically. So for the same reason, this portion of the circumference of this circle is r times theta, which is d theta, or times d theta, which is this little segment here. So that kind of makes sense. The circumference of the individual, there's segments of the circumference of the individual circles make up the sides of dA. So that's why dA is r squared sine theta times d theta times d phi, which when you're just looking at that, it's kind of hard to conceptualize how that exactly works. So yeah, that's where that comes from. So we eliminate the sine thetas, we eliminate that r is from kr. I don't know why did I forget an r? I don't know. It looks like I forgot an r here. Gotta look at this again. It should be r squared. I don't know. I guess it worked out somehow, but I'm pretty sure it's r squared sine theta d theta. Let me look. Yeah. R sine theta dr d theta. Cancel the signs. And from here, honestly, just put it into a calculator, man. You don't want to do this equation. It's like a pain in the ass. It's just not fun, really. It's algebra. I mean, like, obviously, just pause like if you want to actually look at this stuff, and then you finally get the answer, which is mass flow rate, which is this equation. Yep, and that's all for me for today. So, yep, have a good day. Bye bye. Ask me any questions. If you have any questions about problems, if you have any problems you want me to do, whoa, look at that. It's kind of cool. Whoa, that's cool. But yeah, have a good day. Bye.